Okay, so here we are. I think we're on lesson 3 now. We're going to look at more confidence intervals. So we've had a look at confidence intervals before, and we're looking specifically at the Poisson this time. So this is the distribution of the Poisson when it's just got 5, a lambda 5, and this is when lambda is 23. If you look at the formula books, the value for lambda only goes up to 15, and then the formula on the tables and the formula books stop. This is because back when we all didn't have calculators, they had to then use an approximation to the Poisson, and it turns out that the Poisson distribution starts looking very much like a normal distribution curve. Obviously these are discrete values and the normal distribution is smooth and continuous, and we will do continuity corrections, but not yet. So when you're looking at a confidence interval on anything, in particular, confidence intervals have that confidence interval formula, which is just x bar plus or minus z sigma over root n. In this case, when we're dealing with the Poisson distribution, the formula book shows that the Poisson distribution has a parameter of lambda. Lambda is the mean and lambda is the variance. So what we're going to look at is the fact that this formula then that we've had before can be changed to lambda, which in this case is 121, plus or minus our z value for 95% times the square root of lambda. So this is exactly the normal distribution formula. Because lambda is so large, we are allowed to pretend that it looks like a normal distribution, and we use our confidence interval in the same way that we would use the normal confidence interval, because we are assuming that this Poisson can be approximated by a normal distribution, because that's what it looks like when lambda gets large. So this is what we're going to do. We're going to approximate a Poisson distribution with a normal distribution to work out the confidence intervals. So every time you do a confidence interval for binomial or Poisson, we're assuming that the samples are so large that their distributions would look like a normal distribution if you were to sketch it out. So this is the formula. We're saying reasonably large, over 20. If you look in the books and the tables, it's over 15. You can't do anything about. You could suggest, which if you do it in your calculator, where you've done an interval and you calculate it, you could suggest that that's over n, where n is 1, because you've only got one observed bit of information, and that's really the only thing you can do. So this is the first example. Again, I've got all the answers, so we'll have a look at it. A shop sells 96 garden sprays in a particular week. Assume that it will be regarded as a sample. So lambda in this case is 96 for the week. Remember, lambda is over a particular period, and it's this one here, the 4-week period, that will make the difference. So you work out whatever information they give you, whatever you observed is your lambda, your observed lambda, which we sometimes write as lambda hat, would be your observed lambda. So you can only work from what you've observed. You haven't observed lambda in a 4-week period. You've only observed lambda in a 1-week period. So you work out your 90% confidence interval just for lambda, and if you want to work out a confidence interval for 4 lots of lambda, or 4 weeks, then you find your confidence interval for 1 week, and then you times your confidence interval answer by 4. So whatever confidence intervals you do with Poisson, you do with whatever information they give you, you get the result, and then you scale your confidence interval. Hopefully it will explain it as we do some of these questions. So here you are, first one. Really reasonably straightforward. It's a 90% confidence interval, so you want 90 in the middle. You could do inverse normal on your calculator, and here's the answer. They like to see this little bit and then like to see the answer, so that's nice and easy. Second bit, he says an average of 100 sprays per week. 100 doesn't lie, lies within the confidence interval, so there's no reason to doubt his claim. Brilliant. Now do it for a 4-week period. So you found your answer for the 1-week period, you just times it by 4. Give 2 reasons why the confidence. Now, this is another question they like to ask on AQA. Always 2 answers, okay? You've used an approximation, a normal approximation to the Poisson distribution has been used. because you're doing a confidence interval, it is assumed that that's what you're doing. And they end up commenting about the fact that your standard deviation is taken off of your mean. So your standard deviation is also an approximation, because we don't know that the mean's right. So how can we be sure? This one you can do two ways. So I think I may have to talk you through this one. So you can generally go from what you've observed. So in this case, I would go from what I've observed and treat it in the same way. So you have to add up all of what you've observed. So you've observed 15 lengths. So they want to come up with what the mean M, or the mean number of strings per length is, but we've got 15 lengths. So we're going to work out a confidence interval for the 15 lengths that we've got, and then divide our confidence interval by 15 at the end to get the answer. It seems if you can keep that way, it's a much better solution. So that was a total of 22 strings per length. So our confidence interval for the 15 lengths is that, which is then nice and easy. Find your answer, and then it's over here. So work out what the two extremes of this is, and then divide them by 15 to get these two answers. It is the easiest way of doing it. So use the information you have, the lambda, calculate the confidence interval, and then scale up or down as necessary. This was an exam question 1. Pause it and have a go, but I think you see how easy it is. Okay, that one was very easy. Right. Then these are the questions. If you have the book, or you can get hold of the book, use that. The next one is a confidence interval for proportions. Now, proportions are binomial distributions. So we're looking at the probability, the parameter p of a binomial distribution. Okay. So if we're going to use the same confidence interval process, which I think we should, we can have a confidence interval for the mean of the binomial. The mean is NP of a binomial. So it's going to be the mean, x bar, of what we've observed, plus or minus the z value of whatever percentage we're looking for. And this is the variance, so it's times the square root of that. So we're using exactly the same formula because we are, for whatever reason, assuming that the binomial can be approximated by a normal, which it can on specific requirements, which we'll come to. So there is another formula for this, and I will show you the other formula as well. So a newsagent observes that 140 people came to here. So this is, we could say, which I don't know if it is, yeah. We can say, so it's going to be approximated by a normal distribution, and it's got a mean of 140, so NP. P, as it turns out in this case, is 63 out of the 140. So 63 over 40 is our proportion of what we've observed. So 63 over 140 times 140 is 63. Yeah, so we've observed 63 people. 1.96 is the 95% for Z, and then we're just going to use this with P as 63 over 140, which gives you that. Okay. So we do plus or minus that, which gives us that answer. Okay. If you chose to do it, there is another way of doing it. Oh no, there we go. So we get our answer then. So we could work out the two extremes and then divide it by 140, or divide each term by 140 at that point. Because what we're getting is the total for 140p, because we want the confidence interval of the mean, and the mean is NP. So because we want the actual true proportion, not just the one we've seen, our NP, we have to divide everything by N, which is 140 in this case, to get our proper true proportion that we think for the population. You can manipulate the data, or the formula that we have there, to give you this formula. I tried to show how it worked. It's up to you whether you want to use this formula. It's whichever you find easier. So the hat says it's the observed information. But obviously it's got to be the observed information, because we're trying to come up with a confidence interval for the true proportion or probability of the binomial. Here's an example. Please pause it. I'm going to show you the two answers in a minute. So one of the first things I kind of think you should write is once you know it's binomial with 200 and the proportion is 33 out of 200. From that you work out the mean and the standard deviation, and from that you can go straight to the confidence intervals, which are here. So what have we got? 90% confidence interval. So I've got 33, because you do that, n times p would give you 33 as the mean, and then np, n minus p, and you work that out, and then so that's the 90% confidence interval for the mean, which is np, that to that. I'll put square brackets behind it. So if you only want it for the proportion, you would divide these two answers by 200, and that's what you end up with. Calculate 90%. This is doing it in the second method, which is the second formula, where you do the proportion, so that's 33 over 200, and then it's the observed p, 1 minus the observed p, all over 200, and that's all square rooted from that point. You decide. And then accidents occur less than 10%. Well, 10% is smaller than your range, so obviously that's the answer for that one. Give two reasons why the interval calculated is approximate. Same two reasons. Okay, the standard deviation is not exact, and it's a normal distribution approximation. Okay, please read this. Okay. So the value of n is too small for this one to be true, so this is overcome by increasing the size of n, and that is by observing some more Australians. Okay, so your first solution method, we've got 42 is going to be your observed there, which is our mean, because remember, we could write it to make life easier, is b equals n is 112, and the proportion that we've seen, the NP, is 40 over 112. So those two times together gives you, 42, and then you have to do the same formula, ending up with that value, because this is this is for NP. I probably ought to put NP here, and then you divide these by 112 to get your proportion confidence interval for just P. So that's the key thing you've got to remember. So this is the confidence interval just for P. So they've done the proportion, and then it's observed P, 1 minus P over N. It's up to you what you can remember. Final example, is it? Oh yeah, confidence interval thingy. Back to lambda rather than MP. So 94 faults found in 25 roles. Again, pause it please, have a go at this. Oh, sorry, I haven't inserted the answer. That's not, because this is an exact one, that's why. So we're not doing it. Yes, all nasty stuff, blah, blah, blah. Okay, that's that one, nearly there.